Hello, my name is Moj, and I would like to present our work Viewpoint Selection for DermDrone using Deep Reinforcement Learning. DermDrone is a micro-sized quadrotor to fly autonomously in a predefined trajectory around a patient to capture high-resolution full-body images for dermatology applications. The localization of previous version of DermDrone was based on external visual markers, as you can see, customized filler. And we found that human position feedback is a crucial requirement to have a safe and reliable navigation around the patient. To address this problem, our motivation in this work is to propose a localization method with relative positioning feedback with respect to the human body. We propose a localization method based on lightweight human pose estimation, which is built on open pose and single-shot 3D human pose estimation algorithms. We selected this algorithm for two main reasons. First, it is optimized for edge devices like DermDrone's embedded board, and second, it provides accurate joint estimation at high frame rate, which allows us to have real-time localization. According to the active mocap paper, the accuracy of monocular 3D human pose estimation depends on the viewpoint from which the image is captured. According to this fact, our goal is proposing a deep reinforcement learning-based method for determining the best viewpoint given a fixed flight trajectory to improve the localization performance. The related works are categorized in three classes: human-drone interaction, active view planning, and oral-based works. There is no existing works which use oral-based method to improve the accuracy of human pose estimation as localization feedback. We use AirSim plugin in Unreal Engine as simulation environment. We also use cross-RL package to implement the RL algorithms in this project. The agent which is implemented in cross-RL takes an action, and the action is passing by AirGym to the AirSim, which is our simulation environment. After applying the action in the environment, AirGym receives the data, which includes the observation space, and pass it as a state to the agent. So the AirGym acts as a bridge between the agent and the AirSim. We define our RL problem by considering two main tasks. The DermDrone as an RL agent first should select the best viewpoint at each point of the trajectory to maximize the accuracy of localization. And second, it should detect human body pose in all frames. The state space of agent is an RGB image size 96 pixels by 126 pixels, which represents confidence map of joints produced by the human position pose estimation network. The confidence map indicates the probability of the body joints at each pixel locations. Two sets of action space are used to investigate the performance of the agent in each configuration. In the first set, DermDrone can execute three discrete actions: 4-degree increase for the pitch angle, keeping the current pitch angle, and 4 degrees decrease for the pitch angle. On the other hand, in the second set, the agent is also allowed to change the roll angle of camera. Therefore, DermDrone can choose 5 actions to find the best viewpoint: 4-degree increase or decrease of the pitch angle while keeping the current roll angle, keeping both roll and pitch angle; 4 degrees increase or decrease of the roll angle while keeping the current pitch angle. It's worth mentioning that all actions are available at any states along with the trajectory. The agent receives a high negative reward when it fails to detect at least 3 joints. On the other hand, the agent gets a positive reward when the human pose estimation is successful and at least 3 joints are detected. Also, the agent gets another reward term, which is defined by weighted Euclidean distance between the current ground truth position and estimated position. For the network architecture, we use a vanilla network as shown here with 3 convolutional layers which extract the features and are followed by a rectifier linear unit. Then the result is applied to a layer of fully connected network with 512 hidden units. And finally, the second fully connected layer output actions. To solve our problem using deep reinforcement learning method, we implemented the DQN, double DQN, and double dueling DQN algorithms. The plots shows the evolution of the agent in 4 different configurations. Firstly, the 3 policies were implemented with the same state space, reward function, and 3 action space. Then we conducted an experiment to investigate the role of the 2 new actions in the learning process. In this experiment, the agent could rotate the camera in both roll and the pitch angles. The left plots show the final reward in each episode over the training process. All agents failed to get positive rewards during the warm-up steps when the replay buffer was being filled. After a couple of hundred episodes, the reward increased gradually in all algorithms. The comparison between agent with 5 actions and the agent with 3 actions indicates that action in rule didn't improve the performance. The results also indicate that double dueling DQN agent showed a superior learning rate and outperformed both DQN and double DQN. The performance of trained agents show an interesting point that all 3 agents prefer to choose the upper body as a viewpoint, specifically when the drone is flying at low altitude. We believe this preference is because there are more joints in the upper body, which helps the human pose estimation algorithm's efficiency. To evaluate our performance of trained agents, we define 2 terms as quality metrics, which are correlated with the terms defined in the reward function. The first metric is failed frames, the number of frames in an episode that the human pose estimation algorithm failed to detect at least 3 joints. The second quality metric is localization error, the Euclidean error between the ground truth position of DermDrone and its estimated position. The result shows that the agent with random action selection couldn't detect the human body pose in more than 30% of the frames. And the performance of the agents with fixed pitch angles were disappointing. On the other hand, the DQN agent and its variants detected the human pose in more than 96% of the frames. In addition, double dueling DQN had the lowest failed frames, which confirms the functionality of this algorithm. In the localization error criteria, double dueling DQN achieved the best performance, while the fixed 15-degree was the worst. In addition, since the terms of reward function represent the quality metric, we compared the cumulative reward of each agent. The results indicate that our proposed method significantly improved the performance of human pose estimation. Moreover, it confirms that double dueling DQN has the best performance with the least standard deviation. As a conclusion, in this work, we propose DermDrone as a novel total body photography system. We also propose 3D human pose estimation as a real-time positioning feedback for DermDrone's navigation instead of external visual markers. And as a main contribution, we showed promising performance of RL-based viewpoint selection for DermDrone using DQN and its variants. We also showed that the trained agents had a tendency to look at the upper body during the process. Thanks for your attention.